Hello everyone, I'm Professor Chia-Po Wei. Our course will still use remote teaching, and the lecture videos will be available in English. We have weekly quiz, which starts from Monday 8:30 a.m. to 8:45 a.m. Remember to log in the Cyber University. The answer to the weekly quiz will be posted on our course website on Wednesday. If you have any questions about the textbook or the slides, you can use the TA hours, or you can contact me. There will be an examination on May 26th. The examination time is from 18:30 to 20:30. If you have any problem about the examination time, feel free to contact me. The scope of the examination will cover section 3.5, 3.6, and the whole chapter 4. In the previous week, we have learned the definition of a linear transformation. A linear transformation is a special type of function that satisfies two properties, the additivity property and the homogeneous property. In this week, we will cover sections 4.2 and 4.3. In section 4.2, given a linear transformation L, we will learn how to compute its matrix representation A with respect to bases E and F. Once we have the matrix representation, we can use matrix multiplication to replace the evaluation of a linear transformation. A linear transformation can have many matrix representations due to different choices of bases. In section 4.3, we will discuss the relationship between the matrix representations of a linear transformation, which is called similarity. In section 4.2, we often see the notation of the coordinate of x with respect to a basis E. Make sure that you fully understand this notation, otherwise you might have difficulty understanding the material in section 4.2. The notation of coordinates has been introduced in section 3.5. If you are not familiar with this notation, please revisit section 3.5. In section 3.5, we have learned how to compute the transition matrix for two bases. And the way to compute the transition matrix is very similar to the way to compute the matrix representation for a linear transformation. If you are not familiar with how to compute the transition matrix, I would suggest you to revisit section 3.5. In this slide, we will introduce theorem 4.2.1. If L is a linear transformation from Rn to Rm, then there is a matrix A of dimension m times n such that L of x equals Ax for each x in Rn. Here, matrix A is called the matrix representation for the linear transformation. The jth column of matrix A can be computed via the following equality: Aj equals L of Ej. Here, Ej is the jth vector in the standard basis of Rn. Note that the input of L is Ej, which is in Rn, and the output of L is Aj, which is in Rm, because L is a linear transformation from Rn to Rm. To prove theorem 4.2.1, Consider an arbitrary vector x in Rn, which can be expressed as x1 e1 plus x2 e2 plus up to xn en, where e1, e2 up to en is the standard basis in Rn, and x1, x2 up to xn is the coordinate of x with respect to the standard basis. If we apply the linear transformation L to this equality, then we obtain L of x equals L of x1 e1 plus x2 e2 plus up to xn en. Because L is a linear transformation, so L of x1 e1 plus up to xn en is equal to x1 times L of e1 plus x2 times L of e2 plus up to xn L of en. If we denote L of e1 as a1 and denote L e2 as a2 and so on, we can express as L of x as x1 a1 plus x2 a2 plus up to xn an, which can be written as matrix A times the vector x, and a1 a2 up to an are column vectors of A, and the proof is finished. Next, we use example 1 to illustrate how to use the previous theorem for computing the matrix representation of a linear transformation. Define the linear transformation L from R3 to R2 by L of x equals x1 plus x2, x2 plus x3. Note that the input x is in R3, while the output of L is a vector in R2. And our goal is to find the matrix representation of L. According to the previous theorem, we have to compute L of E1, L of E2, and L of E3. To compute L of E1, we substitute x1 with 1, and x2 with 0, and x3 with 0. Then L of E1 becomes 1, 0. Following similar steps, we can compute L of E2 and L of E3. Then, from theorem 4.2.1, we obtain the matrix A, where the first column is L of E1, and the second column is L of E2, and the third column is L of E3. Optionally, we can perform a verification to check whether our solution is correct. To do this, we multiply matrix A with x. If AX is equal to L of x, then this means our solution is correct. If AX is not equal to L of x, then this means you made a mistake during the computation. We know that theorem 4.2.1 only works for a very special linear transformation. The domain must be in Rn, while the codomain must be in Rm. If the domain or the codomain is another vector spaces, such as polynomial or the continuous function, then theorem 4.2.1 cannot be applied. Theorem 4.2.2 is called the matrix representation theorem. This result allows us to compute the matrix representation of a linear transformation, where the domain and the codomain can be arbitrary vector spaces. If E is a basis for the vector space V, and F is a basis for vector space W, then for each linear transformation L from V to W, there exists a matrix A of dimension m times n, such that the coordinate of L of V with respect to basis F equals matrix A times the coordinate of V with respect to basis E for every V. Matrix A is called the matrix representing L with respect to basis E and F, and the jth column of A, denoted as AJ, which equals the coordinate of L of Vj with respect to basis F. We know that matrix A has n columns because the dimension of V is n. Since the basis E has n column, since the basis E has n elements, and matrix A has m rows, since the dimension of W is m, because basis F has m elements. In the bottom of this slide is a figure illustrating the relationship between a linear transformation and its matrix representation. Let L be a linear transformation from V to W. Here V and W can be any vector spaces such as polynomials or continuous functions, and V and W are not restricted to Rn or Rm. The matrix A can be viewed as a function from Rn to Rm, and Rn is the vector space of the coordinate of V with respect to E, and Rm is the vector space of the coordinate of W with respect to F. If you understand the notation, you will know it is not legal to write A times V, because A is a matrix and V is an arbitrary vector, which can be polynomial or continuous functions. It is not legal to multiply matrix A with a polynomial or with a continuous function. The legal notation is A times the coordinate with respect to the coordinate of V with respect to E. Here, the coordinate of V with respect to E is always in Rn, regardless V is a polynomial or a continuous function, and matrix A times a vector in Rn is a legal notation. Similarly, it is not legal to write L of V equals A times the coordinate of V with respect to E, because on the left hand side is a vector in W, which can be a polynomial or a continuous function. On the right hand side is a vector in Rm, because the matrix A times a vector in Rn equals a vector in Rm. Therefore, this notation is not legal. The legal notation is the coordinate of L of V with respect to F equals A times the coordinate of V with respect to E. On the left hand side is a vector in Rm, while on the right hand side is also a vector in Rm. This is a correct notation. Once you know how to write the correct notation, then you can write down the formula for the matrix representation theorem naturally. Once we have the matrix representation A, we can use it to compute the value of L of V. To do this, first compute the coordinate of V with respect to E, which is denoted as x. Then we multiply matrix A with x, and Ax is the coordinate of L of V with respect to F. Then L of V is a linear combination of W1, W2 up to Wn, where the coefficients are from Ax. Ax is a vector in Rm. In this slide, we will prove theorem 4.2.2. Consider a vector V in the vector space V. Then, because V1, V2 up to Vn is a basis for vector space V, and therefore V can always be written as the linear combination of V1, V2 up to Vn. And we assume the coefficients are x1, x2 up to xn. Then we can use the coordinate notation to express this equality. The coordinate notation is the coordinate of V with respect to E equals x1, x2 up to xn. The coordinate notation has been introduced in section 3.5. If you are not familiar with this notation, please revisit section 3.5. Then we apply the linear transformation L to this equality, and we obtain L of V equals L of x1 V1 plus up to xn Vn, which can be written as x1 times L of V1 plus up to xn times L of Vn, because L is a linear transformation. Our next step is to express L of Vj as the linear combination of W1, W2 up to Wm. Because if this step can be achieved, then we are able to obtain the coordinate of L of V with respect to F, where W1, W2 up to Wm is a basis of F, and the coordinate of L of V with respect to F is the left-hand side of the matrix representation formula. And if we obtain this term, then this term can be written as a matrix times a vector, and the proof is finished. We know that L of Vj is in vector space W, and W1, W2, Wm forms a basis for the vector space W. Therefore, L of Vj can always be expressed as the linear combination of W1, W2 up to Wn. And we assume the coefficients are A1j, A2j up to Amj. Then we can use the coordinate notation to express this equality. That is, the coordinate of L of Vj with respect to f equals a1j, a2j up to amj. And we denote this vector as aj, and aj is a vector in Rm. Next, we substitute L of Vj into the above, and we obtained L of V equals x1 times parentheses a11w1 plus up to am1wm plus up to xn times parentheses a1n w1 plus up to amn wm. After some arrangements, L of V can be written as the linear combination of w1, w2 up to wm, where the first coefficient is x1 a11 plus up to xn a1n, and the mth coefficient is x1 am1 plus up to xn amn. Then we can use the coordinate notation to express this equality. That is, L of V, the coordinate of L of V with respect to f equals the vector. And after some arrangement, this vector in Rm can be written as a matrix A times a vector. Here the matrix here A1, A2 up to An are the column vectors of matrix A, and x1, x2 up to xn is a vector in Rn, which is the coordinate of V with respect to E. And our proof is finished. You don't need to memorize the proof of theorem 4.2.2, but you should know how to use the theorem. That is, given a linear transformation L and two bases E and F, you should know how to use the matrix representation formula for computing the matrix representation A. The key idea for computing the matrix representation is very similar to the way we compute the transition matrix between two bases in section 3.5. If we can properly select V from vector space V, then we are able to recover the matrix representation A. If we select V as V1, V1 is the first element in the basis E, then the coordinate of L of Vj with respect to F is the first column of matrix A. If we select V as V2, V2 is the second element in the basis E, then the coordinate of L of V2 with respect to F is the second column of matrix A. Similarly, if we select V as Vn, Vn is the nth element in the basis E, then L of Vn, then the coordinate of L of Vn with respect to F is the nth column of matrix A. Once we have A1, A2 up to An, we will have the matrix representation A. Next, we will use example 5 to illustrate how to apply theorem 4.2.2. Let L be the differentiation operation that maps P3 into P2. because L is the differentiation operation, so the highest order of the input polynomial will be reduced by 1, and hence the codomain is P2. Given two bases E and F for P3 and P2 respectively. Here, E and F, in this example, E and F are standard bases in P3 and P2 respectively. Our goal is to compute a matrix representation for L. We will use the matrix representation formula to find the matrix representation. The key is to select V as elements in basis E. In our example, the elements in basis E are x squared, x, and 1. We want to compute the coordinate of x squared with respect to f, and we also want to compute the coordinate of L of x with respect to f, and we also need to compute the coordinate of L1 with respect to f. First, we compute L of x squared. Because L is the differentiation operation, L of x squared equals 2x. Then we need to express 2x as a linear combination of basis f, because we want to compute the coordinate of L of x squared with respect to f. It is easy to do this because f is a standard basis. 2x equals 2 times x plus 0 times 1. Hence, the coordinate of x squared with respect to f equals 2, 0. Next, we can compute L of x, which equals 1, because L is the differentiation operation. Then we need to express 1 as the combination of basis f. Then 1 is 0 times x plus 1 times 1. Hence, the coordinate of L of x with respect to f is 0, 1. Next, we compute L of 1. Because L is the differentiation operation, L of 1 equals 0, and 0 equals 0 times x plus 0 times 1. Hence, the coordinate of L of 1 with respect to f equals 0, 0. Then, according to theorem 4.2.2, 2, 0 is the first column of matrix A, and 0, 1 is the second column of matrix A, and 0, 0 will be the third column of matrix A. We know that the order of the column vectors in matrix A is based on the order of basis E. If the order of basis E changes, then the order of column vectors of matrix A also changes. Below we show that the coordinate of Lx squared with respect to f is the first column of matrix A. If we select V as x squared, then the coordinate of x squared with respect to E is 1, 0, 0. Because if we express x squared as the linear combination of basis E, then x squared equals 1 times x squared plus 0 times x plus 0 times 1. Hence, the coordinate of x squared with respect to E is 1, 0, 0. And the matrix A times 1, 0, 0 becomes A1. The A1 is the first column of matrix A. Similarly, we can prove that the coordinate of L of x with respect to F equals A2, where A2 is the second column of matrix A. And we also can prove that the coordinate of L of 1 with respect to F equals the third column of matrix A. Thus, A equals thus the column vectors of the matrix representations are A1, A2, and A3, which has been computed already, and our example is finished. Optionally, we can perform a verification to check whether our solution is correct. Let P be a polynomial in P3. So P can be written as a times x squared plus bx plus c. And the coordinate of P with respect to the standard basis E is a, b, c. Because L is the differentiation operation, L of P equals 2ax plus b. And the coordinate of L of P with respect to F. F is the standard basis in P2. So the coordinate of L of P with respect to F is 2ab. Now we can verify the matrix representation formula. We multiply matrix A with the coordinate of P with respect to E, which is ABC. Then the result is a vector in R2, which is 2a and b. And 2ab is exactly the coordinate of L of P with respect to F. Therefore, our solution, matrix A, indeed satisfy the matrix representation formula, and hence our solution is correct. In this slide, theorem 4.2.3 and corollary 4.2.4 considers a spatial linear transformation where the domain is Rn and the codomain is Rm. For this spatial linear transformation, the column of the matrix representation can be computed via the matrix multiplication. And corollary 4.2.4 states that you can use the reduced row echelon form to compute the matrix representation. In fact, you can ignore the two results because they are only spatial cases of theorem 4.2.2, the matrix representation theorem. In fact, if you are already familiar with theorem 4.2.2, you can use it to solve any calculation problems in this section. But for completeness, I will quickly go through theorem 4.2.3 and the corollary 4.2.4. Let E and F be two bases in Rn and Rm respectively, if L is a linear transformation from Rn to Rm. Then and the matrix A representing L with respect to E and F, then the jth column of matrix A equals the inverse of matrix B times L of Uj. The column vectors of matrix B are elements of the basis F. The dimension of matrix B is m times m, and therefore B is a square matrix, and L of uj is a vector in Rm because the output of L is in Rm. One consequence of this theorem is that we can determine the matrix representation by computing the reduced round echelon form of an augmented matrix. The augmented matrix is B1, B2 up to Bm, L of U1, L of U2 up to L of Un. The augmented matrix has m rows and has m plus n columns. Corollary 4.2.4 states that if A is the matrix representing L from Rn to Rm with respect to bases E and F, then the reduced round echelon form of the augmented matrix B1, B2 up to Bm and L of U1, L of U2 up to L of Un is the identity matrix and the matrix A, where matrix A is the matrix representation of the linear transformation L. Next, we discuss example 6. Our textbook uses corollary 4.2.4 to compute the solution for example 6, while I will present another method. I will use the theorem 4.2.2, the matrix representation theorem, to compute the solution. Let L be a linear transformation from R2 to R3 and is defined by this equality. Our goal is to compute the matrix representation of L with respect to E and F. E is a basis in R2, and the elements are U1 and U2, which are given vectors. F is a basis in R3, with elements B1 and B2 and B3, where B1, B2, and B3 are given vectors. I will use the matrix representation formula for computing the matrix representation A. The key is to select V as elements in basis E. So I will select V as U1 and select V as U2. First, we compute if we select V as U1, then we need to compute L of U1. Because U1 is 1, 2, so we replace x1 with 1 and x2 with 2 and compute L of U1 as 2, 3, 2, 3 minus 1. Then we need to express L of U1 as the linear combination of B1, B2, and B3. Because we want to compute the coordinate of LU1 with respect to F. So we express L of U1 as the linear combination of B1, B2, and B3, where the coefficients are A11 are denoted as A11, A21, and A31. Note that this equality gives rise to three equations, and there are three variables to be solved. After solving the three equations, we obtained A11, A21, and A31 as -1, 4, and -1. And A11, A21, A31 is the coordinate of L of U1 with respect to F, which is the first column of matrix A. Next, we select V as U2 and compute L of U2. Because U2 is 3, 1, so we replace x1 with 3 and x2 with 1, and therefore L of U2 becomes 1, 4, and 2. Next, we need to express L of U2 as linear combination of B1, B2, and B3, because we want to compute the coordinate of LU2 with respect to F. L of U2, so we express L of U2 as the linear combination of B1, B2, and B3, where the coefficients are denoted as A12, A22, and A32. Note that this equality corresponds to 3 equations. From the 3 equations, we can solve the 3 variables A12, A22, and A32, which are -3, 2, and 2. A12, A22, A32 is the coordinate of L of U2 with respect to F, which is the second column of matrix A. Since we already computed the 2 columns of matrix A, this example is finished. Exercise 6 is in page 207 of the textbook. You can use this exercise to test whether you understand how to apply the theorem 4.2.2 to compute the matrix representation. And the answer of exercise 6 can be found at the end of the textbook. We have finished section 4.2, and we are going to study section 4.3, which considers a linear operator. For a linear operator, the domain and the codomain are the same vector space, and therefore the matrix representation of a linear operator is a square matrix. A linear operator can have different matrix representations due to different choices of bases. Theorem 4.3 characterizes the relationship between 2 matrix representations of the same linear operator. Theorem 4.3.1 is called the theorem of similarity transformation. If E and F are 2 bases for the same vector space V, and let L be a linear operator from V to V, and let S be the transition matrix from basis F to basis E, and if A is the matrix representing L with respect to E, and B is the matrix representing L with respect to F, then the relationship between matrices A and B is B equals S inverse times A times S. We know that the transition matrix is a square matrix because basis F and basis E are of the same dimension, and a transition matrix is always non-singular. In the bottom of this slide is a figure illustrating the theorem of similarity transformation. matrices A and B are the matrix representations of the same linear operator L. Matrix A is the matrix representation of L with respect to basis E, while B is the matrix representation of the linear operator L with respect to basis F. The matrix S is the transition matrix from basis F to basis E, and therefore S inverse is the transition matrix from basis E to basis F. Theorem 4.3.1 states that B equals S inverse times A times S. Next, we prove theorem 4.3.1. In view of the matrix representation theorem, we know the first equality for matrix B and the second equality for matrix A. Because S is the transition matrix from basis F to basis E, and we have the third equality. And we also know S inverse is the transition matrix from basis E to basis F, so we have the fourth equality. Next, we will prove the following relationship, where the first equality is due to the first quantity in this slide, and the second equality is due to S inverse is a transition matrix from basis E to basis F, and the third equality is due to the second equality in this slide, and the fourth equality is due to S is a transition matrix from basis F to basis E. Now we have proved the premises of B minus S inverse AS times the coordinate of V with respect to F equals the zero vector for all V in the vector space. This condition will imply B minus S inverse times A times S equals the zero matrix. To see this, we can select V as the first element in basis F. Then the coordinate of V with respect to F equals the first element in the standard basis of Rn. And therefore, this equality will imply the first column vector of B minus S inverse AS equals the zero vector. Similarly, if we select V as the second element in the basis of F, then the coordinate of V with respect to F is the second element in the standard basis of Rn. And then this equality will imply the second column of B minus S inverse AS equals the zero vector. Following similar steps, we can show the column vectors of B minus S inverse AS are all zero vectors, and therefore B minus S inverse AS is the zero matrix, and thus B equals S inverse AS, and the proof is finished. Next, we introduced the concept of similarity. Let A and B be two square matrices of dimension n times n. B is said to be similar to A if there exists a non-singular matrix S such that B equals S inverse times A times S. We have the following remark. If B is similar to A, then A is also similar to B, because A can be written as the inverse of S inverse times B times S inverse, and because S inverse is also non-singular, so A is similar to B. Because of remark 1, it doesn't matter whether A is similar to B or B is similar to A. Thus, we may say A and B are similar matrices. From theorem 4.3.1, if A and B are two matrix representations for a linear operator L, with respect to different bases for V, then A and B are similar. Because if A and B are matrix representations of L, then there is a transition matrix S such that B equals S inverse times A times S, and therefore B and A are similar. Next, we discuss example 2. Let L be the linear mapping from R3 into R3, defined by L of x equals X, where A is a given matrix of dimension 3 times 3. Matrix A is the matrix representation of L with respect to the standard basis in R3. And our goal is to find the matrix representation D of linear transformation L with respect to basis F, where y1, y2, and y3 are given vectors. y1, y2, and y3 forms a basis in R3. There are two methods to compute matrix D. The first method is to use the matrix representation theorem. And then, by the definition of D, we know L of x with respect to F equals D times the coordinate of x with respect to F for all x in R3. Then we will select x as the elements in basis F. So we will select x as y1, y2, and y3. First, we compute L of y1. Then, by definition of L of y1 equals A times y1. Because matrix A and y1 are given, after some computations, we know A times y1 equals the 0 vector. And we will express 0 as the linear combination of y1, y2, and y3. Because we want to compute the coordinate of L y1 with respect to F. Then 0 can be written as 0 times y1 plus 0 times y2 plus 0 times y3. And therefore, the coordinate of L of y1 with respect to F is 0, 0, 0. Then, by the matrix representation theorem, the first column of matrix D is L of y1 is the coordinate of L of y1 with respect to F. Next, we compute L of y2. By definition of L of y2 equals A times y2. And after some computations, we know A times y2 equals y2. Then we need to express y2 as the linear combination of y1, y2, and y3, because we want to compute the coordinate of L of y2 with respect to f. Then it is easy to see that y2 equals 0 times y1 plus 1 times y2 plus 0 times y3. Therefore, the coordinate of L of y2 is 0, 1, 0. Then, by the matrix representation theorem, the second column of matrix D is 0, 1, 0. Next, we compute L of y3. By definition of L of y3 is A times y3. After some computations, we obtain A times y3 equals 4 times y3. Then we need to express L of y3 as the linear combination of y1, y2, and y3. Because we want to compute the coordinate of L of y3 with respect to f, it is easy to see that 4 times y3 equals 0 times y1 plus 0 times y2 plus 4 times y3. Therefore, the coordinate of L of y3 equals with respect to f equals 0, 0, 4. And 0, 0, 4 is the third column of matrix D. The second method to compute matrix D is to use the theorem 4.3.1. Divide matrix Y by horizontally stack y1, y2, and y3. Then matrix Y is the transition matrix from basis F to basis E. And because matrix A and matrix D are both matrix representations of the linear operator L, and therefore, in view of theorem 4.3.1, D equals Y inverse times A times Y. And since matrix A is given and matrix Y is also given, because y1, y2, and y3 are given vectors. Therefore, matrix D is obtained by computing Y inverse times A times Y. Next, we discuss exercise 5. Let L be the operator on P3 defined by L of P equals x times the derivative of P plus the second derivative of P. There are 4 cases to be solved. In case A, we need to find the matrix A representing L with respect to the standard basis in P3. In case B, we need to find matrix B representing L with respect to basis F, which is another basis in P3. In case C, we need to find a matrix S such that B equals S inverse times A times S, where matrices A and B are computed in cases A and B. In case D, we need to calculate L superscript n of P. Here, L superscript n is to apply the linear operator n times consecutively, and the input polynomial P is of the form a0 plus a1 times x plus a2 times parentheses 1 plus x squared. In case A, we will use the matrix representation theorem to compute the matrix representation A, we will select the polynomial P from basis E. That is, we will select P as 1, x, and x squared. First, we compute L of 1. By definition of L, L of 1 equals x times 0, because the derivative of 1 is 0, plus 0, because the second derivative of 1 is also 0. Hence, L of 1 equals 0. Then we need to express L of 1 as the linear combination of basis E, because we want to compute the coordinate of L of 1 with respect to basis E. Clearly, 0 equals 0 times 1 plus 0 times x plus 0 times x squared. Therefore, the coordinate of L of 1 with respect to E is 0, 0, 0. Next, we compute L of x. By definition of L, L of x equals x times 1, because the derivative of x is 1, plus 0, because the second derivative of x is 0. Therefore, L of x equals x. And we need to express L of x as the linear combination of basis E, because we want to compute the coordinate of L of x with respect to E. Clearly, x equals 0 times 1 plus 1 times x plus 0 times x squared. Therefore, the coordinate of L of x with respect to E is 0, 1, 0. Similarly, we can compute the coordinate of L of x squared with respect to E as 2, 0, 2. Then by the matrix representation theorem, we know the first column of matrix A is L of 1, is the coordinate of L of 1 with respect to E. And the second column of matrix A is the coordinate of L of x with respect to E, while the third column of matrix A is the coordinate of L of square with respect to E. In case B, we need to compute the matrix representation B, which can be solved in the same way as done in case A. In case C, we need to find a matrix S such that B equals S inverse times A times S. Clearly, S is the transition matrix from basis F to basis E. Therefore, S need to satisfy the transition matrix formula. That is, the coordinate of x with respect to E equals S times the coordinate of x with respect to F for all x in P3. We will use this formula to compute the transition matrix, and the key is to select x as the elements in basis F. Thus, we will select x as 1, x, and 1 plus x squared. If x is 1, then we will compute the coordinate of 1 with respect to E. Therefore, we will express 1 as the linear combination of basis E. And because E is the standard basis, it is easy to do this, because 1 equals 1 times 1 plus 0 times x plus 0 times x squared. And therefore, the coordinate of 1 with respect to E is 1, 0, 0. Second, we select X as the second element in basis F, which is X, and we want to compute the coordinate of X with respect to E. So we need to express X as the linear combination of basis E, and clearly X equals 0 times 1 plus 1 times X plus 0 times X squared. Therefore, the coordinate of X with respect to E is 0, 1, 0. Similarly, we can obtain the coordinate of 1 plus X squared with respect to E, which is 1, 0, 1. And therefore, we have obtained the three columns of the transition matrix, which is 1, 0, 0, and 0, 1, 0, and 1, 0, 1. In case D, we will compute L superscript n of P, which means to apply L n times consecutively. We will use the matrix representation formula for computing L. That is, the coordinate of L of P with respect to E equals A times the coordinate of P with respect to E for all P in P3. Then one can derive that the coordinate of L superscript n of P with respect to E equals the nth power of A times the coordinate of P with respect to E. This formula is for basis E using matrix representation A. Similarly, we can derive the formulation for basis F using matrix representation B. Now we have two formulas for computing L superscript n. Which formula should we use? Clearly, the second formula is easier because matrix B is a diagonal matrix. A diagonal matrix means the only non-zero elements appear on the diagonal of the matrix. We know that the coordinate of P with respect to F is A0, A1, A2. And the nth power of B is easy to compute because B is a diagonal matrix. After matrix multiplication, we obtain 0, A1, the nth power of 2 times A2, which is the coordinate of L superscript n of P with respect to F. Hence, we know the superscript of L. Hence, we know L superscript n of P equals 0 times 1 plus A1 times X plus the nth power of 2 times A2 times parentheses 1 plus X squared. Next, we discuss exercise 8. Suppose A equals S times lambda times S inverse, where lambda is a diagonal matrix with diagonal elements lambda 1, lambda 2 up to lambda n. In case A, we need to show A times Si equals lambda I times Si for I from 1 to up to n. If we multiply both sides with S, then we obtain A times S equals S times lambda. If we let S1, S2 up to Sn, be the column vectors of matrix S, then we will have this equality. Note that AS1 is the first column of AS, and ASN is the nth column of AS, while lambda 1 S1 is the first column of S lambda, and lambda n Sn is the nth column of S lambda. Therefore, we have finished the proof of case A. The result of case A implies that if A is similar to matrix lambda, where lambda is a diagonal matrix, then we will have A times Si equals lambda I times Si, which means Si is an eigenvector of A corresponding to eigenvalue lambda I. In case B, we need to show if x equals alpha 1 times S1 plus up to alpha n Sn, then the case power of A times x equals alpha 1 times the case power of lambda 1 times S1 plus up to alpha n times the case power of lambda n times Sn. And the proof can be done by mathematical induction, and is left to you as an exercise. In case C, suppose the absolute value of lambda I is less than 1 for I from 1 to up to n. What happens to the case power of A times x as k approaches infinity? If the absolute value of lambda I is less than 1, then we know the case power of lambda I approaches 0 as k approaches infinity. Then by case B, we know the case power of A times x equals the right hand side, and because the case power of lambda 1 and the case power of lambda 2 and the case power of lambda n approaches 0 as k approaches infinity. Hence, we know the case power of A times x approaches the 0 vector when k approaches infinity. The result of case C implies that if the absolute value of each eigenvalue of A is less than 1, then the case power of A times x will approach the 0 vector as k approaches infinity, regardless the value of x. In this slide, I have selected some well-known results regarding similarity transformation, and I have provided detailed solutions for each exercise. By studying these results, you can enhance your understanding about similarity transformation. Finally, I have selected some exercises for you to practice. I have selected exercises in section 4.2 and section 4.3. The answers of these exercises can be found at the end of the textbook. After studying section 4.2 and 4.3, make sure that you understand how to apply the matrix representation theorem for computing the matrix representation of a linear transformation. Also, make sure that you understand the concept of similarity transformation, which is the relation between two matrix representations of the same linear operator. Feel free to leave comments regarding the video or the slides. Don't hesitate to ask if you have any questions.